Greetings. Today we'll be focusing on Chapter 13.2, Types of Solutions and Solubility. To understand this chapter, something you should know is that an aqueous solution is a solution in which water acts as a solvent. Now diving into the main idea of this chapter, solubility. Solubility is the ability of a substance, the solute, to form a solution with another substance, the solvent. If you look down below, you see a spoon filled with sugar dumping into a cup of tea. Now, solubility is exemplified in the process of making tea when sugar is added to hot water. As the sugar is introduced to the hot water, its molecules are enveloped by the polar regions of the water molecules, breaking the intermolecular bonds holding the sugar together. This always allowed the sugar molecules to disperse throughout the water, forming homogeneous solution. However, there is a limit to how much sugar can dissolve, known as the saturation point. Once this point is reached, no more sugar can dissolve without altering the conditions. Therefore, the process of sugar dissolving in hot water to make tea illustrates the fundamental principles of solubility. Taking a deeper dive, when you have two opposite particles such as protons and electrons, or cations or antions, each particle moves towards each other because their potential energy decreases as their separation decreases, according to Coulomb's law. What is Coulomb's law, you may ask? First, we must begin with who is Coulomb himself. Coulomb was a French physicist named Charles Augustin de Coulomb. His law states that like charges repel and opposite charges attract, with force proportional to the product of charges and inversely, which is displayed by the formula below. To get a better understanding, we could take a look at the figure ahead. Represented by the blue dots are gas particles of the element neon. Separated by a divider are the red dots representing gas particles of the element argon. Now, if we were to remove this divide, we can see that the neon particles and argon gas particles mix together, making a homogeneous mixture. This leads us to entropy. Entropy is the measure of an energy randomization or energy disorder within a system. If you look to the left, you see low entropy. The blue particles are separated and the red particles are separated as well. They have some distance in between. If you look to your right, you see a high entropy where the blue particles and red particles are mixed and mingled together. Energy dispersal. Energy dispersal, a combination in which tiny particles of one component disperse into another. All of this relates to energy dispersal. If you look down below, an example. Chemical energy dispersal and combustion, such as in a car engine, involves the conversion of stored chemical energy in fuels, like gasoline, into heat, mechanical works, sound, and light energy. During combustion, the bonds within the fuel molecules break, releasing energy in the form of heat, primarily, which is converted into mechanical energy to drive the vehicle, along with sound and light energy as byproducts. This process exemplifies how chemical energy is effectively dispersed and transformed into various useful forms of energy. Unfortunately, that is all the time that we have today. I thank you for watching and hope to see you soon. Like what you hear? Please feel free to leave a comment down below, or maybe subscribing.